Hey guys, it's Michael with Breaking Concepts, and in this video we're going to talk about discrete logistic growth model. Previously, we've talked about what discrete functions are, discrete time models. Now, the reason why there's a change of word here is because it is a logistic growth model. Basically, kind of models what a population growth is going to look like under a realistic condition. What I mean by realistic growth model is what you guys are about to see. But basically, this is a mathematical difference equation, okay? Make sure it's not differential because differential is another thing. It's a mathematical difference equation, which means it's periodic, used to model population and dynamic over distinct generation and time step, right? Again, these are discrete, and I love highlighting that. Discrete is so important. Okay, so before I give you guys the formula of the discrete logistic growth model, there's two quick concepts that we have to talk about before. So here's the first idea. So we've learned that in previously NT plus 1 basically is equals to our R times our NT. Our R is our per capita growth rate, and NT is our current population. So this is how to find the next population. This time I wanted to think a little bit deeper. How to actually find the next population. So in other words, where did our NT plus 1 actually comes from? Well, to look for our next population, we have to first find what is our current population, because without the current population, we're not going to have our next population. So we have to find our current population, addition to the increase of our population. That could be, and that most likely comes from birth. So you can see here birth, and the minus, we want to minus the outflow population, which is, how many people died. This formula is a little bit intuitive, just for a quick summary. So basically, to find our NT plus 1 population, we have our current population, in addition to how many new populations have grown, right? We have birth and all that. But at the same time, we have to minus the death rate. So this maybe is our new NT plus 1, right? Current population plus birth minus death. So in order to define birth and death, so we have number one, our beta constant. Our beta constant is the per capita birth rate, which means within per capita, right, per person, what is the birth rate looking like? If the birth rate is 1, it means per person, they're going to have 1 offspring. Okay, so this is what beta means. And again, this is per capita. So to find the entire population of inflow population, all we have to do is just take beta times our NT. The same idea for the outflow population. So here we have mu, which is the constant per capita death rate, right? So all we got to do is take mu times NT. So this gives us the population for outflow. And summing it up, basically we have NT plus 1 equals to NT plus our beta times NT, our inflow population, minus our mu times NT, which is our outflow population. So we have a formula like this. And this is important because understanding the concept of inflow and outflow is going to help us understand what the discrete logistic model means in some parts. And we're going to talk about that in a second. And to unpack our second concept here, we're going to talk about what is a non-overlapping generation. So in real life, sometimes insects, they die right after reproducing. So in this case, we can sub our mu, right, our per capita death rate. So what is the per capita death rate? It's 1. Because per capita, per person, what is the probability that they'll die, or what is the rate that they'll die is 1. So using our formula, we have NT plus 1 is equals to NT plus our beta times NT, birth rate, minus our mu times NT. What do we know about mu? We know mu is actually equals to 1. So basically, we have NT plus beta NT minus NT. And seeing NT minus NT, you guys can cross. So NT plus 1 is going to equals to just beta times NT, right? Crossing these out. And that's the conclusion. So what that means is our next population is simply going to be equals to our new produced offspring. So this is what we've learned so far. And I'll actually call the left-hand side concept 1 and the right-hand side concept 2. In the future, I'm probably going to refer to these two concepts, and I hope this makes sense to you so far. So we've seen all those equations in the past, right, where the discrete time models keep growing infinitely. But in reality, that is not what's going to happen within a population. And the reason why, as you can see here, is there are limitations such that populations cannot grow indefinitely or infinitely. So imagine you have a pond here. And the maximum capacity for the pond is 3. So now, let's say I have one fish here, And in this space, there's infinite resources, there's infinite, space to go. There isn't really any competition. So let's say this fish, for some reason, it can reproduce with itself, and some of the species in the real world actually does that. So let's say that the fish can actually reproduce with itself. So we have another fish now. So there's 2 fish in total within the tank. In this case, nothing's gonna happen because both have enough food. They still haven't reached the maximum capacity yet. And let's say we have another more fish. We have 3 fishes in total. Now we're at the maximum, but nothing's gonna happen because they still have enough resource, enough space to live. But if we add an extra fish, right now, it's the total number of fish is gonna be 4. 4 is greater than 3. There's going to be problems. Number one, there'll be fighting over food, land, whatever. So population will start to decline from 4 to 3, or maybe this got hurt, and this fish also got hurt from the fight, and he also died. So the population dropped down to 2. So in reality, there's boundaries. The reason, because number one, we have this maximum available resource. So the pie is that big, and if there's too many people, we can't give it to everyone. And number 2, we have the habitat limitation, right? We need space to move. So here we have the discrete logistic growth model, and this is the formula. Now, please do not think that the logistic growth model is this one. This is just the one that we've shown in the past, the discrete time model. And the discrete logistic growth model is actually this one, okay? And I put this equation here just to show you what's the difference. We actually derived the discrete logistic growth model from our previous equation. So looking clearly, actually, both equations are similar, but the R is actually equal to the entire chunk of meat inside. So the first major change that we see in R is, number one, there's the R. There's a small letter R. Okay? And number 2, we have something called K. So here's a quick definition. So our big R is our per capita growth factor. But at this time, our small r is our intrinsic growth rate, which is basically the maximum possible per capita growth rate when the population is very small and the resource is unlimited. What is important, I want to talk about this intrinsic growth rate right now so that you can take home the concept. So basically, using our pond and fish example, when there's absolutely no competition, what do you think the growth rate is? It should be the maximum, right? Imagine you're born rich, you're probably Elon Musk's son or whatever. You have unlimited resource, and for you to reproduce, you don't have to think about food, you don't have to think about shelter. You can reproduce as much as you want as the highest maximum capacity. Going back to the fish concept, as there's more competition of mates maybe, there's more competition of food and resource, this is going to start to drop, right? Because it's not as easy for you to reproduce anymore. So intrinsic growth rate, you can kind of think about it as how easy it is for you to reproduce. Well, that's why it's saying it's the maximum possible per capita growth rate when the population is very small and the resource is unlimited. Okay, and K here is actually our carrying capacity. Okay, and let's look at K. K here is a constant, by the way, which is our carrying capacity. A carrying capacity is basically, what is the maximum population that a habitat can hold. Well, back on our fish concept, our fish and pond concept, it was 3. But remember, K is actually the population. It's the amount of population that the habitat can maximally carry. So let's first take a look at this fraction here, NT divided by K. So what that means is basically, what is our current population over our carrying capacity, right? Remember, the K is also population, is an amount. So let's say our maximum, so let's say we are in a pond where the maximum capacity is 1,000 fish. And let's say our current pond has only about 800 fish. So what you'll get a fraction, basically 800, by the way, divided by 1,000, and you'll get actually 80%. So for this percentage, what we can infer is what is the percentage or fraction has we taken off of our carrying capacity. So we're at 80% max, right? Are we at 20% max? Are we at only 0.5% max, or are we at 100% max? Now 100% max was simply when NT is equals to K. So when NT is equal to K, let's say it was 1,000, right? So it's going to be 1,000 divided by 1,000, and then we'll get 100%. And this is important because writing this concept, look at this chunk of meat here. We have 1 minus, right? This is the fraction minus the NT over K, right? And if the NT over K is 1 in total, then you have 1 minus 1 equals to 0. So 0, then the entire thing here is going to be equals to 0. So if the entire thing is equal to 0, then R is going to be just equals to 1. R equals to 1. And writing on that, if we know that R is only equals to 1, then this entire thing, again, is going to be equals to 1. So NT equals to 1 times NT. That simply means NT plus 1 equals to NT. Now, this is probably the most important concept here because this is the concept of equilibrium, which is another video that I'm going to make in the future. But basically what it's trying to say is, no matter what, the current population is going to be equals to our population for tomorrow. Basically, what that means is our population number today, tomorrow, and so on and so forth is going to stay constant. We're at an equilibrium. So this is what NT plus 1 equals to NT means. So from our experimentation, we know that if NT is equals to K, then R is going to be equals to 1. And R going to be equals to, and if R going to be equals to 1, NT plus 1 is going to equals to NT. Simple as that. And this means that we're at equilibrium. Right? Which means that the future generations could be T plus 2, T plus 3, T plus 4. It's going to all be equals to NT, if you think about it. Now, if R times 1 minus NT over K is small, well, first of all, how do we make it small? We make it small by having NT actually approaches to K. NT approach to K. And I can give you an example. Let's say K is 10 and NT is 9. So we have 1 minus 9 over 10 as 0.9 times R. I'm just using this thing times R. Then we know that the R is going to be 1 minus 0.9. That's 0.1 R. So remember R? R is basically our maximum potential growth rate. So we have so much potential. We have the maximum potential. But this time, because our NT is approaching K, so basically we're reaching to the maximum capacity, our potential isn't there anymore. It's actually 0.1, right? It's only 10% of our maximum potential. That's basically what it means. As we approach to our maximum capacity, we can't really grow that much or that rapidly. So now we have number 3 is if our R times 1 minus NT divided by K is similar to R. So what this means is that we can, let's say NT is equal to 0. So R times 1 minus NT, which is 0 divided by K, it could be whatever. 0 divided by anything is going to be 0. So R times 1 minus 0 is equals to R. Instead of like the previous one where you have 0.1 R, here we had the absolutely maximum potential for growth. But NT is equal to 0. The current population cannot, unfortunately, be 0 if you want to grow something. But what this is trying to say is when NT is very small, very, very small, right? We're just starting out with population, maybe we have a maximum capacity of 1 million and we just started out with like 1 or 2 fish. And realistically, what they should have is they should have the maximum potential for growth, right? There's no competition. There's no competition for mates, no competition for habitat, space, resource, whatever. So they should be growing at the maximum capacity at that time. So unfortunately, I don't want to make this video too long. I want to keep it bite-sized learning and easy and digestible. So I'm going to have to make a part 2. So yeah, stay tuned and thank you so much for watching this video.